Where's our crowd? To go get them for lunch.
Yeah.
Good afternoon, everybody. And we'll get these guys like stuff to stop talking eventually. Welcome to the session on PFAS. I'm Steve Zembe with Sanborn Head. I'll give myself a quick intro because I'm going to do the first talk here. What we have are 4 scintillating talks. Great people talking. I know some of them already, and I'm looking forward to meeting others. And we're talking about per and polyfluoroalkyl substances, and they're taking a lot of different industries by storm. Oil and gas is going to be one of those industries because of their role as a drinking water contaminant. So let's see here. There's my bio, but what you need to know about me is I've been doing environmental consulting for 35 years. I specialize in health risk assessment. And so I work on a lot of projects with chemicals in soil, groundwater, and air, and trying to figure out exposure to those. Started getting involved in PFAS back in the 2016 timeframe when it hit the Northeast. My office is in Burlington, Vermont, so I'm a fish out of water here in Texas. But we have a lot of experience with PFAS in the North. We have some of the more stringent standards in the country in states like New Hampshire and Vermont, Michigan. Got represented here also. So that's kind of what I do. And just quickly, Sanborn Head is a 170-person company with mostly concentrated in the Northeast, now Pennsylvania and Denver, and provide a lot of different services. If you think of a site remediation company with a couple of extra services, that's Sanborn Head. We have some real specialized areas. You can read them there, things like vapor intrusion, chemicals, things of that sort. Oh. I'm going to give a little bit of PFAS background. How many people are very familiar with PFAS? How many people are not familiar at all? Okay, these slides are for you. Everybody else can go to sleep for the first 4 slides. I guess PFAS started getting a lot of publicity in the sort of 2015, 2016 timeframe. EPA came out with a lifetime health advisory of 70 parts per trillion for groundwater for 2 chemicals, and that built on work that was started by really one attorney. Up a lot with the Taft Law Firm in Ohio, and he kind of went on a crusade really to get information out of DuPont about the Parkersburg, West Virginia factory that made Teflon. But in making Teflon, they also put PFOA up into the air, one of the PFAS compounds deposited locally within 20 miles of the plant and contaminated, worked its way through soil and contaminated groundwater in a lot of different communities. That story is well told in the movie Dark Waters. Anybody seen Dark Waters? It's actually, put it on your list. It's a good movie to watch. It's kind of, I liked it. I don't agree with everything in it, but I did like the movie. But also The Devil We Know. And there are 2 links. There'll probably be copies of these slides available. So you can look at those links and find either a trailer or a short documentary that's a little more factual. It's called The Devil We Know. Needless to say, EPA has been active on PFAS slowly. The PFAS action plan came out in 2019. Didn't do a whole lot, but the October 2021 PFAS roadmap, and I'll talk a little more about this, is important. And just to give you a sense of how PFAS is gaining popularity, I did a Google search the other day, 33 million hits on PFAS. Here's a historical reference. How many of you guys get this? They lose to the Beatles at 192 million. But so it's not quite Beatles status yet. Financial implications, particularly even for the oil and gas industry, there have been lawsuits going out there. I'm not familiar with this lawsuit. I just know it exists. But Valero has sued on for basically the anticipated cost of remediation to deal with PFAS, essentially. It's in multi-district litigation in South Carolina. I don't know what the status of this is. Other companies have not followed suit in the oil and gas industry. Valero is kind of out, as far as I know, out on its own, but there are some serious financial implications associated with PFAS. And now to really start the background, PFAS is a class of at least 5,000 chemicals, 8,000 by some people's estimations, but they share 2 properties. They're a 2-part molecule. The molecule part on the left side there is a carbon fluorine tail. And you basically take a basic alkane, carbon hydrogen thing, and take the hydrogens off and completely fluorinate it in the perfluorinated case. That chemical by itself will be rather benign and not interact with anything. It repels fats, it repels water, which makes it a great waterproofing agent, or you could put it in coatings. This part of the molecule makes it what we call functional. That when you put it in water will dissociate and forms an ion, and then these chemicals act like surfactants. They like to sit on the surface of water. And when we talk about AFFF, aqueous film forming foam, the whole purpose of that is to have this chemical sit on the surface and suffocate a flame, if you will. That's how the foams will work. These compounds vary in chain length, fluorine saturation, and precursors. The difference between a per and a polyfluorinated chemical is some of those fluorines are hydrogens on a polyfluorinated version. Because the carbon fluorine bonds are very, very strong, these chemicals are essentially indestructible perfluorinated compounds under environmental conditions. So they're going to be around, and they're sometimes called the forever chemicals. Some varieties of what these things look like. There's sort of two groups of perfluorinated compounds. They're the sulfonic acid. The sulfonic acids characterized by that functional group. The difference with the carboxylic acids are the functional group at the end. They vary in chain length. It would be an 8-carbon compound for Pfas. There's the, I don't have PFOA up there, but there's the 6, the 7, and the 9 in this case for the carboxylic acids. The compounds that replaced some of the long chain perfluorinated compounds have basically more complexity. They have some bonds here that you can break down. So that 8,2-fluorotel or alcohol, for instance, will have some carbons or carbon-hydrogen bonds that make them degradable. But guess kind of what some of these things degrade into? Some of these compounds. So environmental degradation can produce more PFAS compounds. Quick regulatory summary. Prior to May 2016, when the Lifetime Health Advisory came out at 70 parts per trillion, there were a few states that were already interested in PFAS. You probably recognize Michigan, and Minnesota is being leading states there because they had some of the more important and more contaminated sites. New Jersey had the only low standard at that point, below 70 parts per trillion. Once the 70 part per trillion number came out, more states started looking at this, and more state toxicologists started looking at it. So many states have standards for groundwater or for drinking water in the 10 to 20 part per trillion range now. And 10 to 20 parts per trillion is a hard number to measure and certainly a hard standard to meet. I did mention drinking water, and I'll come back to that. I wanted to talk a little bit about what's coming. And EPA has laid out a pretty aggressive schedule for actually actions under various bits of legislation. The first one would be, and they're all laid out in the PFAS action plan. There are deadlines and some hints as to what might be going on there. The first one is going to be the hazardous substances designation. It's probably going to apply to only PFOS and PFOA. Those are the two most studied compounds the EPA knows the most about. And those are the industries, including petroleum refineries and terminals, that are likely to be affected by hazardous substances designations. I think the second thing that's going to be important is going to be ambient water quality criteria. Because right now, the focus is on drinking water. And if you're not affecting somebody's drinking water, well, you know, if a tree falls in the forest and you don't hear it, does it matter? If the drinking water isn't affected, not so important. But surface water is going to be harder for people to meet because everybody interacts with surface water. And you can see sort of some of the things that are coming. They're going to be are already calls in NIPT's permit renewals to add PFAS to the list of things you sample in some states. It can only be a little bit of time until some of those standards get set, and they're going to be real effluent limits. Two industries that are going to be affected by this immediately are going to be, or in the near field, will be the organic chemicals industry and also metal finishing, chrome platers in this case. Other industries that the EPA is considering are things like pulp and paper, textile mills, commercial airports, and landfills and wastewater treatment plants are also being studied pretty hard by EPA in terms of effluent limitations. What scares me the most is the next bit under maximum contaminant levels. EPA has been kicking that around for a long time. They're committed to coming out with primary drinking water regulations under the Safe Drinking Water Act. And if the hints or any on the toxicology are valid, those numbers are going to be a lot lower than 70 parts per trillion. Because EPA, in a meeting with its Science Advisory Board, presented toxicity data. And the toxicity data they're presenting was 10,000 times lower than, more stringent than the current value that they use to get 70 parts per trillion. Even if they back off on that by 2 orders of magnitude, take 100 factor lower, you're down in the non-detect range for PFOA and PFOS. So there's going to be a lot of benzene, trichloroethylene. EPA is probably going to set up an MCL at essentially the detection limit. So if you detect it in water, you're going to have an issue on the drinking water side. It's my guess. One last thing I mentioned, or I didn't mention there, but the TRI is going to affect present facilities. TRI is focus release inventory. That's already been required to some extent, so I don't have the TRI on this slide. Sorry about that. But there is the TRI inventory that will affect air emissions, and Dave is going to talk a little bit about air emissions and how you might have to measure those coming up. So I just want to put that one out there because it affects a lot more PFAS and it affects operating facilities and processes that are going on right now. On the health effects side, I wanted to say a little bit about PFOA in blood because you, I, and everybody in this room probably has measurable levels of PFOS and PFOA in our blood. And that's, I think, what scares people. If you ask me, how toxic are PFAS, you get a lot of range of opinions on that. Some people think it's very toxic. Some people are not toxic at all. I think only God really knows how toxic PFAS are. But the one thing that we can say for certain is these compounds do bioaccumulate in our blood. And even though we technically have kind of banned them in the US in the 2005 timeframe under the stewardship program, they still show up in our blood. And if you look at the pattern, this is for PFOA. Important thing about this chart, by the way, is that these are background levels, about 2 parts per billion, not parts per trillion, but parts per billion in an average person's blood. If you have PFOA in your drinking water, you're looking at 10 to, I don't know how many more times. It's about 100-to-1 ratio between what you have in your water and what will show up in your blood in terms of bioconcentration. So this is why drinking water is a big deal. You have higher PFOA levels in your blood or higher PFOS levels in your blood. One individual in Michigan down gradient of a PFAS waste landfill essentially had 3,200 parts per billion in their blood of PFOS. Person's still alive. The good news on this is that levels are coming down in our blood. And those of us who were alive in the 1998 timeframe, you can only imagine about 1990, these curves kept going, what our levels must have been in blood. But PFOS, this is a 2-axis system here. PFOS has gone from about 30 parts per billion in our blood down to about 5. And PFOA has gone from about 5 down to 2. So there have been marked decreases. There are forever chemicals, but we do excrete them. We don't metabolize them, we excrete them slowly. And as long as our intake is lower than our excretion rate, we'll continue to see these decreases in our blood. Those are starting to level out though, because there are always going to be background exposures. The latest look at toxicology really is starting to look at multi-generational models, just to give you a hint of where EPA might go with this. Immunological effects and effects on the development of the immunological system in children are thought to be one of the more important endpoints. And what EPA is now looking at, because the highest exposure that you get is if you're a nursing child. You basically take mom's PFOA, she transfers it through breastfeeding to you. And much smaller body weight, much higher concentrations in their blood. So a lot of the standards that for people who are looking at these pharmacokinetic models are based on trying to limit the level in young children so that immunological effects don't occur. Whether these really occur, it's kind of uncertain, but that's what they're targeting. One interesting thing here is that the ratio of what the mom has in her blood, 4 micrograms per liter, compared to what's in her drinking water, which is about 12 parts per trillion, is a ratio of 300. It kind of tells you that these models are a little on the conservative side. That should be more like 100, 150 for a typical person. UCMR sampling in Texas, since I'm in Texas, the levels weren't too high. UCMR is the Safe Drinking Water Program's attempt to sample what they call emerging contaminants, which are like PFOA PFOS are called emerging contaminants at times. This was a national sample in large public water systems, and EPA at that point was comparing to the 70 parts per trillion number. There were no exceedances of 70 parts per trillion in Texas. So Ucmr 3 was not such a big deal. It was a bigger deal in other states. What it typically found was downgrading of military sites that used a lot of AFFF. You had high levels in drinking water in some systems. And when I move on, Ucmr 5, by the way, is going on very soon. They're going to be 29 PFAS measured as opposed to the 6 PFAS. So there are going to be more detections of PFAS, and EPA is going to have to decide what to do about those. I wanted to mention surface water standards because when EPA establishes the ambient water quality criteria, they establish two things. They establish the direct toxicity to aquatic organisms, but they also look at effects on human health, assuming that that surface water can be used as drinking water and as a source of fish in many cases. And so the floor on an ambient water quality criteria, they're not going to be driven by ecological effects because they're not terribly toxic to aquatic organisms. They will be driven by human health. And so whatever EPA comes out with as an MCL is going to be kind of the floor for a ambient water quality criteria. And it could get worse. The states that have looked at ambient water quality criteria and gone down this road trying to come up with human health-based levels, have started looking at fish ingestion. And just like people, PFOS will bioaccumulate in fish, PFOS compounds. So that's going to be driving some things and could lead to, again, low part per trillion numbers, maybe down to non-detect if we get those MCLs down there. And wanted to emphasize this was a number for surface water, 0.05 parts per trillion or 50 parts per quadrillion that was proposed in Minnesota to be applicable as a surface water standard based on fish ingestion for some cases. This is an actual Minnesota document. These things are coming, they're not going to be good. So if we think about the industry, what's mostly going to be affected is your effluent, your NIPD's permits, because they're going to have to meet those ambient water quality criteria a few years down the road. I'm going to talk a little bit about some data in New Jersey. New Jersey sampled some of their lakes. The purpose of looking at this data are kind of to show you how ubiquitous PFAS are in the environment. You go out and sample for them, there's a good chance you'll find them. They might not even be yours. They might just be background. And these numbers are basically, I want to emphasize PFOS here because I think that's where we're going to get some stringent ambient water quality criteria. This is surface water. Most of the sites had PFOS levels in surface water, many of them above the state standards, which are sitting at about 10 parts per trillion. A couple of non-detects, including a reference site in Echo Lake. They also measured sediments and measured fish, which is probably the most interesting part. So in surface, sediments, the only site that did not have PFOS was this reference site. Every place else found PFOS in sediments. Many of these sites having no known sources of PFAS. And when they looked in fish, even in the reference location, they found PFOS in the fish. I have no idea how that PFOS got to the fish. With a high bioconcentration factor, you can easily see how it could be in water at non-detectable levels and in fish at detectable levels. Direct relevance to the industry. And I'm doing okay on time. Good. I'm rushing through some stuff, so I'm happy to go back to any slides, by the way. But I want to talk a little bit how this gets relevant to the oil and gas industry. I've already hinted at it with the ambient water quality criteria they're going to be hitting. One thing I'd like to mention is back in the 2004 timeframe, when the phase out of PFOA and PFOS was going on, there was some source inventories done. And one of the inventories that was done was for AFFF, aqueous film forming foam, which is used to basically put out oil fibers. What I've circled on here is the fact that oil refineries and petrochemical industry, things associated with petroleum, accounted for a good bit of the foam that was out there at the time. Those industry has a lot of this stuff in place. That's kind of the first point. And where does it get used? Well, the main use of it, bolded there, is firefighting. It's there to put out fires if you have fires, and it's very effective at oil fires, which is why it is required in NFPA codes quite frequently in petroleum-related installations. Also, every airport, of course, would have AFFF in its inventory. There are some other places PFOA or PFAS could show up. Teflon lined pipes would have impurities associated with them, like PFOA. That could be a minor source of PFAS. Also, it's mentioned in the literature that drilling fluids could have PFAS in them. I don't think that's true in the US. I want to ask people. That seems to be a thing that might have happened in China, but I don't think it's that common in the US, if at all. But there are some references out there that people point to that. It's probably not that important to this industry in the US. But the firefighting is the main one to think about, and the AFFF foam systems that would be in place to put out fires. A little bit about foams. There were several types of foams over the years, and they were evolving based on EPA's regulations and phase out of PFOS and PFOA. Old plastic foam, the first stuff that was invented in the 1960 to 2002 timeframe, made by 3M, was called light water. And light water had 1 to 2% PFOS in it. So you typically applied it as a 3% concentrate, as it says, so dilute it by 30-fold with water. So mix 1 part foam, 30 parts water, and you're going to get concentrations in the high parts per million level for what we would have PFOS in that water. So that's why this is a significant source when it gets used. But it's not only when it gets used, it's practice. People started practicing putting out fires with this stuff in fire training facilities, at refineries, and also at other locations. So there were years when it was probably used, and nobody really cared about the releases because it was largely thought to be non-toxic. You can see these pictures of kids covered in foam at firemen's fairs because they could do that. They could spray the foam on the kids, and it's kind of fun. And well, it's really not that immediately toxic, and that was not a major source of exposure. I would have enjoyed it. But anyway, I'd still do it too. But anyway, for legacy fluorotelmer AFFF started coming out in the 70s. It was kind of the competition to light water, but it had the advantage that it didn't have PFOS in it directly. It used other more complex PFAS, but some of those PFAS chemicals will break down to PFOA. So if you're at a refinery that used foams and you sampled your groundwater, for instance, you might find PFOS or PFOA in different places based on when you might have used some of these or used some of these foam systems. Modern fluorotelmer AFFF has very, very low levels of PFOA in them, but they're part per billion levels because it's a trace contaminant. It's not meant to have chemicals that bleed and degrade into PFOA. But the other foams were used for quite a bit of time, and so there's a lot of legacy foam out there. And I didn't mention this earlier, but there are transformations, and what you want to, of course, avoid would be formation of PFOS and PFOA, but a lot of these compounds will degrade into these compounds. So even though these are replacement compounds, they're thought to be less toxic from a direct toxicity standpoint. In the environment, they will actually degrade into the PFAS we don't want. So there are continuing sources out there of these chemicals in soil and groundwater. Found a little bit, just a couple of case study examples, and it's going to be the end of my talk. But potential release scenarios, AFFF active use to fight fires. We've had refinery fires, like some refineries have had. Good chance you used foam on it, maybe even on minor incidents because it puts out fires pretty quickly. It really works well. And if I was a risk assessor doing cost benefit, I'd probably say save more lives than it ever affected in other ways by getting those fires out quickly. But system testing and fire drill areas are probably the more common sources that were probably used historically by people. Of course, losses to leaks from systems always. And one thing I wanted to emphasize is spray drift, that you think of the foam storage system being a certain location, the fire drill area being a certain location. I'll show you a case study where that source gets a lot bigger than you think. Because when you're spraying foam into the air, especially in a high temperature fire environment, stuff gets up into the air and travels a little bit. So the release is going to be bigger than just the immediate area. The other thing to think about is wastewater and groundwater treatment discharge, and those can be related. If you're practicing with foam, chances are that wastewater or the runoff went into your wastewater treatment system, would have been a discharge to the wastewater treatment plant. But we're seeing some sites now where VTEX remediation is going on. There's a pump and treat system for removing high levels of VTEX compounds at a particular refinery. and that they're pulling out PFAS at the same time. And when they put it through the treatment plant, it removes the PTEX compounds, but it's hard to treat for PFAS. So the PFAS kind of just goes straight through the system. And so they're now an effluent discharge for PFAS inadvertently from the pump and treat system. So you need to probably watch for that one too if you have active remediation going on. A couple of noted instances, and I'm taking these from the literature. There was a facility in Australia called the Australia Waste Oil Refinery. What these people did, they're not a typical facility, but they would take used oil and try and refine it. And they took all sorts of things. And one of the things they took from other refineries was barrels of wastewater. We'll just give you our PFAS-laden wastewater, and you can deal with it, right? Well, they put it into their wastewater treatment plant, put it into the creek. The people noticed it, took, sample measurements, citizen-type sampling, found high levels in the creek, and this facility got in a lot of trouble for that. There are 22 times the drinking water standard in the creek, but the levels that they were measuring in their wastewater in retrospect were in the hundreds of thousands of parts per trillion of PFOS. So that's the kind of numbers you'd probably see from an active release, at least. So that was one facility. I want to mention airborne deposition, and Kevin will like this slide. This is a facility in New Hampshire. It has nothing to do with the oil and gas industry, but it has everything to do with airborne deposition. Much like the facility that DuPont had in Parkersburg, West Virginia, this plant did a slightly different process. It was coating textiles and coating it with Teflon. And in doing that, Teflon, to get the Teflon to go out evenly in the Teflon bath, you add PFOA to it. And when you put that coated fabric, wet coated fabric through dryer, guess what happens to the PFOA? It goes off into the air as either an aerosol particle, probably. Well, that leads to stack emissions. And stack emissions, because we're talking about parts per trillion levels in groundwater, you can get to part per billion levels in soil pretty easily from this mechanism of airborne deposition. And so these are instances of individual private drinking water wells, which there are a lot of in New England, that we're comparing to the levels of the New Hampshire standards. Anything in yellow basically is above the New Hampshire standard. And what to notice here is there's the factory. This is kind of a hillside over here. This is the river flowing south. So these are all very much up gradient or uphill from the source. There's no way that this stuff gets here except by air. This is a kind of a documented air site. And this also shows some complexity because you had another potential source here, an airport, and you've got another potential source down here being a waste disposal area, a landfill. So separating these sources out with forensics can sort of be done, but methods aren't really great for that at this point. But that's what you might be faced with is you might go out, sample for PFAS, and you might have background because in Vermont, we've measured PFAS in rural soils that have nothing to do with any sources. They just got there from long range transport, maybe from West Virginia and other places. It's not hard to get to part per billion levels in soil as a background condition, or if you have an active source, much higher levels. And if you got parts per billion levels in soil, if you think about feeding groundwater at parts per trillion levels, you've got a source that could be 100 years of contamination leaching out slowly to affect groundwater. So these atmospheric deposition sources are real. This facility, by the way, violated no permits. If you take these PFAS emissions and probably realistic estimates of them and think about them, how they would have been regulated at the time, they would have been regulated as particulate matter emissions. That's kind of what it was. And you look at the number of tons per year, it's probably a couple tons per year at most, emissions from these facilities. So well under any significant emission threshold. So just kind of a case of you get what you get sometimes. This is a direct example of a refinery. So this is maybe the most relevant example I have. It's an oil refinery, the largest one in Norway, and they have their own fire training area. And they started sampling around the fire training area, and they started looking for PFAS levels. And they're measuring at various depths in the soil and various distances from the facility. So up to, for instance, 91 meters away. The fire training area is not that big. It's not 270 feet. But at 270 feet away, 90 meters, they're measuring 6,000 parts per billion in soil. 1 part per billion might be background. So these are relatively high levels. They're measuring PFAS off into the woods on this facility. And again, it's from that concept of maybe some water runoff, but also from spray drift, because they're measuring it in each and every direction from the facility. The take-home lesson on that is that these sources might be bigger than you think when you go and start sampling. It might just not be the area where you apply the AFFF. Some site characterization and management issues. Finishing up my last two slides here. If you already haven't done it and you operate a refinery, probably you're going to go and look at your historic foam stocks. That's a two-edged sword. You might want to know what you used in the past, you might not, depending as to your approach to potential litigation down the road. But if you're trying to separate yourself out from other sources, having a good sense of what you use might be useful, because it could tie to some of the compounds that you see in groundwater and soil. If you do have a release of this sort, it'll probably be pretty obvious, but there may be stuff coming on site from other areas that could complicate it. Conceptual site models, you got to consider air, soils, surface water, and groundwater. And frankly, our fate and transport models are not that good. There's uncertainty, at least factors of 10, I would say, and a lot of those models, Kevin might talk about those, diss on your models before you present them. But there's a lot of uncertainty in modeling. Certainly the conceptual site model is important, because we got to understand how it moves through the environment. But those are in some cases research areas as to how PFAS behaves in soil at this point. Old traditional models are good, but they may not work so well in some cases. They might work fine, but you got to take a lot of data if you're going to support that conceptual site model. You got to sample multimedia to understand it, is I think where I would go with this. Drinking water resources are going to be your most important thing. Again, if you're not near a drinking water source, like somebody's private wells and things like that, you can have a lot of PFOS in groundwater, it doesn't matter. If you're near a discharge area of surface water stream, though, I would start worrying about that a little bit, because those are going to become potential drinking water sources subject to water quality criteria. I'd say that there's been some talk about vapor intrusion of PFAS. I think that's overstated a little bit based on some transport considerations, but that's out there and people might talk about it. The issue that you're probably going to face, though, is getting rid of your old AFFF. You can now get those low fluorine or even no fluorine formulations. I don't know if any of those are approved yet, but you can certainly get away from the PFOS and PFOA precursors. And if you do that, you're going to try and take that AFFF out to somebody. Maybe in Texas they still take it, but a lot of areas are very sensitive to taking used AFFF. But we're certainly seeing that in the Northeast that commands a premium. The military has tried to destroy it through incineration, and I think that actually works, but there's been some controversy associated with it. So you can't take it to a hazardous waste incinerator. It's not even hazardous waste yet, but it will be soon. But you can't even take it to, most incinerators won't take it at this point. A lot of landfills will not take it. So prices are going to be going up for getting rid of that stuff. So if you got a chance to do it now, do it while you can, I guess is my advice. And the last thing would be, other compliance issues, restrictions on your wastewater treatment systems. Don't be surprised if your NIPT's permit has you sampling for PFAS in the future, and that down the road there might be some effluent limitations associated with that. Historic releases to sediments, those could be a legacy issue also, depending on where your outfall was and things of that sort. And ultimately, this is going to enter into site remediation programs. It already is in Texas. The standards aren't that stringent at this point. But if MCLs come into being at low part per trillion numbers, it's going to make a difference. Conclusions, I think that PFAS is not going to go away. I'm not going to wake up tomorrow and your worst dreams are going to come true. This is going to get worse before it gets better. And CERCLA hazardous substance declarations are going to have far-reaching effects once they're called PFOS and PFOA, if they are designated hazardous substances, that will enter a lot of different regulations. At this point, states are still leading the charge, especially in the Northeast and some other states. And again, those fire suppression systems, both legacy use and even maybe potential use, could be your most significant sources in the oil and gas industry. Watch the soils. They're not big from a risk assessment perspective, but they're very important from fate and transport perspective. And Potential treatment. I think the NIPD's permits are going to be the big thing. I think that's all I have, and I have time for 10 minutes. So let's open it up for discussion. Said a lot. I presented a lot, I know.